Thank you so much for the introduction. And let's begin. So the underwater world is largely unexplored. And consequently, underwater autonomous robots have become extremely fundamental for a variety of purposes. These include environmental monitoring, ecological surveying. And if we could connect these with aerial drones, we could have a better bird's eye view and situational awareness of our world. However, in order to enable this, we need to somehow communicate between these two different worlds, so in the air and below in the water. And how can we do that? Well, currently, we can have our underwater robot periodically resurface purely to communicate data, but this is inefficient as we have to interrupt our current task just to communicate. Second, we could deploy a network of relay buoys. So in the air, these might be communicating using RF and acoustic waves underwater. However, there's a logistical and deployment overhead associated with this as well. So there's a need here for some direct method to communicate between the air and the water that is efficient and free of these different types of overheads and has a few other benefits. So let's look at some of the communication mediums we can kind of consider here. First, RF. This is kind of the go-to, right? Wi-Fi, 5G in the air are fantastic. However, if we consider the case of underwater, we're going to get this severe attenuation. And this does depend on the wavelength, but even at low frequencies, we can have attenuation about like 3.5 to 5 decibels per meter, so only allowing short wireless links. Second, acoustic communication. Just purely due to the physics, these waves will reflect off the air-water boundary, meaning we can't support a direct link using purely acoustic communication. And a really interesting prior work saw these two mediums here, and they said, well, we can send out acoustic data underwater, which is going to cause these small displacements on the water surface. We can then sense those with the millimeter wave radar. However, this is unidirectional, again, as we have those RF waves. And it's also low throughput, so only a few bits per second. And a less discussed medium is using light. So light, as it passes through the air-water interface, only less than 10% of that power is lost. Additionally, it's bidirectional, so we can send this light from underwater to the air or the air to underwater. And for the purposes of this paper, we consider laser light, not only because it's really cool, but also because it has a sparse spectrum footprint, so its energy is contained to a very small frequency range, which means we can tune the laser wavelength to the wavelengths that attenuate the least underwater, in this case, the blue to green range here. And also gigahertz modulation. So laser light has been shown to actually communicate between the air and the water at gigabits per second speeds and multimeter throughputs. However, all of these prior works consider static interfaces, so no waves, no environmental dynamics, and also benchtop equipment, which really does not work in this mobile-oriented approach. So let's look at some of the challenges with realizing a robust practical laser link. Number one, wave dynamics. So you can see here we have our wave, and as it moves throughout the scene, the beam underwater is going to oscillate, and this is due to hitting different incident points on the water surface, and then the refraction underwater is going to oscillate. So this translates to a link unavailability up to almost 70%, which means that we're not going to be able to communicate data. And this is not good enough for a wireless link. Second, beam steering. We have this narrow laser beam that we need to somehow steer around obstacles and also to the intended target. And existing methods of steering laser beams are bulky, they're expensive, and not very mobile-oriented. And finally, ambient light. So we're sending data over this light channel, but we also want to support the outdoors. However, as the sun's rays kind of come down, hit our ocean surface, our luminance is going to be really large, so hundreds of thousands of lux. And what this means is that our sensor could easily be saturated, allowing us to not see those faint laser pulses. And to solve all of these challenges, we present our framework AmphiLight. And we have two main components here. We have our basic link design, including our transmitter and receiver. And then we have our ultrasonic sensing to sense the wave condition. And to begin with, I'll focus on our basic link design first. Within our transmitter specifically, we have a lot of components. But to begin with, I'll talk about our beam steering. So we have three main requirements here. Our beam steering has to be full hemisphere, so we can steer anywhere around our transmitter. It needs to be accurate, so fine-grained, and also portable. And a potential candidate is gimbal-based steering, so using like free space optics, LiDAR. And these are cool, right? They can do a full hemispherical steering range, but they're not very accurate, and they're also not very portable. So this kind of led us to look at MEMS-based systems, like a MEMS-based mirror or an acousto-optical deflector. However, these clearly cannot achieve a full hemispherical steering range. In fact, they can only do a few degrees or even milliradians. But they are fine-grained and they are portable. So obviously what we want to do is somehow combine these two into a single portable package that is both fine-grained and coarse-grained, depending on what we need. And to accomplish this, we utilize a fisheye lens. And typically these are used in photography. What they do is they take in light rays from an entire hemisphere and concentrate them down into a very small angular output range. And then you'll have your image sensor somewhere around the image plane. And to instead steer out to an entire hemisphere, we reverse the orientation. So we send light out to this small angular range to achieve a full hemispherical output range. This is a completely passive component. So if we combine this with a MEMS mirror, then small movements of our mirror will allow us to achieve a full hemispherical steering range. We also throw a triplet lens in between these two components. And this is to correct the beam angle incident orientation onto the fisheye lens and also clean up the beam quality. And then small movements of this MEMS mirror allow us to again achieve that full hemispherical steering range. So for typical MEMS mirrors, we can expand this plus or minus, for instance, 14 degree steering range to plus or minus 90 degrees on 2 axes. And again, all of these components, except for the laser diode, are completely passive, and the MEMS mirror, right? But this MEMS mirror, it's fast, it's robust, and extremely portable, and also accurate. Okay, so with our transmitter design in mind, let's move on to our receiver. And the challenge here is we need to somehow extract those low-level laser signals amidst strong ambient light conditions. And to validate this, it was a hot day up in New Hampshire. We went outside, we measured the spectrum footprint of our laser light, and we can see here it is confined to that very narrow wavelength range. But we also measured the sunlight. This spans the entire visible light spectrum, as we would expect. But if we were to compare the signal strength of that laser light to the visible light spectrum, we have a super low SNR, so almost negative 13 dB, which is way too low to support any sort of communication scheme. But because of the sparsity of the laser's footprint, we can add a narrow optical bandpass filter around it. This only considers light now within this really narrow 4 nanometer region. And by doing that, we kind of zoom in here. We can kind of see this region. We can increase our SNR up to almost 4.4 dB. So a huge improvement from a purely passive optical component. And that's what they look like on the bottom right there. They're really small. OK, so we solved our basic link challenges. Let's now move on to our sensing. So as we saw before, as this wave moves throughout the scene, our beam underwater is going to refract. And this is the same if we were to reverse the orientation. The naive solution is, well, we can just expand our laser beam, and then regardless of that refraction, some light will always hit our receiver. But this is very inefficient, as we're wasting power steering to a region where we know the receiver is not located. Consequently, we want to take a more proactive approach. So step 1, we want to sense the wave condition. And then step 2, compute the optimal incident point on that reconstructed wave to steer our laser beam to. We're going to focus on step 1. And initially, we considered using infrared, like with a Kinect, for instance. But these rays would pass through the water surface, much like our laser light. And then we also considered using RF. But again, we want to support both orientations. So those waves would attenuate if we were trying to reconstruct the water surface underwater. So instead, we use ultrasonic sensing. And we build this array here, which can sense the wave condition up in the air. But it's also bidirectional, as these waves will reflect underwater as well. It's impossible, though, right, to sample, or at least extremely impractical, to sample every single point on this ocean wave surface. So instead, we want to build an array of ultrasonic sensors, which can sequentially trigger, and they can compute the height from each sensor to the water surface. And then given these discrete samples, we can feed them through to a wave model and create our interpolated surface. And for our implementation, we used a bicubic surface model as our wave model. And this can be replaced in the future with more advanced models, like going straight to the physics of dispersion. But for simplicity and its flexibility, we chose this for our implementation. And here we can see h of xy is the height of a single sensor at some xy coordinate. And alpha, these are our surface parameters. There's an issue, though. Typically, for low-cost ultrasonic sensors, they're all at the same frequency. What that means is we must wait for all of them to return their distance measurements before we can reconstruct our surface. But we can reduce this with the forecasting method. So we can assume that the wave in question is periodic, so we can compute the Fourier transform over some historical data, extract that dominant frequency, and then as our sensor readings come in, we're continuously updating our wave model. So we reduce this latency from the time it takes for the entire array down to waiting for a single sensor. OK, so we've reconstructed our wave. Now we need to figure out where to steer to on that wave to hit our receiver. And for any incident point on this reconstructed surface, we can draw array M from our sensing array to that point, which is going to refract underwater. We have our array R. And the relation between these two in the surface normal is governed by Snell's law. And the key here is that we can also draw a ray from that incident point down to our receiver, which has an angle theta with our refracted ray. So then the goal becomes, how can we minimize theta to have our refracted ray hit the receiver? We kind of flip this around a little bit and formalize it. So now we say, let's maximize cosine of theta, right? And there's a few constraints here. So first, the refracted light's direction. Snell's law, again, relating alpha and beta relative to the surface normal. And also the surface normal itself, which we can compute from our sensor array data. And we solve this optimization problem with gradient ascent, which we can do in less than 1 millisecond for both the reconstruction and the incident point finding once we have the historical data. OK, let's move on to our implementation. So this is our transmitter. I was extremely happy that we fit everything in this waterproof tube, and it looks pretty cool. And for our modulation scheme, we use dark light, which is from a prior work of our lab, and it's a low duty cycle OPPM scheme. And the key here is that typically for laser diodes, you need to have active cooling, so their central wavelength does not shift too much as they heat up. But we instead chose to use a low duty cycle to keep the heating issue basically just removed from the equation. Next, we have our receiver, also fully waterproof. And for our photosensor, we used an ultra-sensitive silicon photomultiplier with a very large active area. You can see the picture over here. And to sample these nanosecond laser pulses with a high enough resolution, we did use a gigahertz level oscilloscope, but I'll mention how we can replace that with a more mobile-friendly approach in a few slides from now. And here's our ultrasonic array. So we laser cut, actually, this plastic sheet to hold all of these different sensors. And we connected all of them to an Arduino to record the data, and we connected that to our controller. So our system evaluation. We focused on two main aspects here. First, the link performance, and also the link robustness. These are our two main testing scenarios. We have a water tank where we could generate arbitrary waves, and also a swimming pool where we test the static case. First, let's look at throughput. So we took our link, set it up in this tank here. We have our transmitter and our sensing array in the air and our receiver underwater. And we generated waves that were about 10 to 12 centimeters in peak-to-peak amplitude and approximately 1 hertz. And next, we wanted to compare 3 different methods. So no sensing, aka we're just steering straight down and the waves move throughout the scene, without our forecasting method, and then with our forecasting method. And so in the no steering case, we were transmitting at about 5 megabits per second. So we were getting about half throughput here, so 2.6 megabits per second. Without forecasting, we could jump a little bit to 3.5. But with forecasting, we saw a huge improvement up to 4.2 megabits per second. So I think the big takeaway is that without our active sensing, our link was disconnected almost 48% of the time. But with our forecasting, we improved our connection time to 83%. Next, we evaluated the range of our link. So we went to our college pool. We put our transmitter in the air and our receiver underwater. And then each bar that's going to show up is going to be a different water distance and then the air distance on the x-axis. And we can see here that across all of the distances that we measured in this 3.1 meter joint range, we achieved a throughput greater than 5.03 megabits per second and a bit error rate below 0.01. Now, this is not the extent, the total distance that our link can achieve. I don't know if you can tell from this picture, but we started to hit the ceiling of our pool. So we do expect that the complete range would be a bit farther. Next, we look at ambient light robustness. So we took our link outdoors in a really harsh environment, so 74,000 lux, and compared that to the indoor case with lights off, which was about 7 lux. In indoors, we could achieve a 0-bit error range distance of about 6.5 meters. And outdoors, we could achieve 6.1 meters. And I think this is really important because this is the harshest conditions compared to the ideal conditions. And there's only about a 40 centimeter discrepancy here. So this really does show the efficacy of using passive optical filtering to block out that ambient light. And finally, wave robustness. So we wanted to test our methodology here on some controlled wave conditions. That's pretty difficult without like a wave tank, which we don't have to generate arbitrary waves. So instead, we wanted to evaluate this on some simulation results. So specifically, we simulated a wave with a sine wave, which is used typically in like the graphics community. And to figure out the parameters for this model, we built a buoy. We sent it to Barbados with our robotics lab. We measured some ocean characteristics on a calm day. So we saw peak-to-peak amplitudes that were about 2 to 20 centimeters, and wave frequencies between about 0.1 and 3 hertz. So for our simulation, we looked at the effective peak-to-peak amplitude of these waves. And the y-axis here is our connection ratio, so how often is our link connected. And across the board, our forecasting method performed much better than the no-sensing case. However, notably, the reliability did start to decrease at large amplitudes. And finally, wave frequency. I think the improvement here from the no-sensing case is pretty clear. Overall, we were able to achieve a reliability of 75% regardless of wave frequency within this range. And this can further be improved with faster wave sensing and reconstruction. Future work. So there's still a good amount that we have to do. Number one, mobility. We assume throughout this that our transmitter and our receiver are at fixed known locations. However, we have these robots that are moving around the scene. So what we would like to do is reuse that laser beam that's kind of being steered around the room for passive sensing to figure out where each of the robots are at all times. And also in the cases of occlusion, adapt the link because they are able to move. Second, our analog receiver. So as I mentioned before, we needed an oscilloscope. However, we can replace that gigahertz level ADC with a comparator-based method on this analog front end. And we currently have a prototype that can achieve about 2 megabits per second receive data at that rate. However, we want to get that up to the extent that we're transmitting at, which is 5 megabits per second. Wave sensing. As I mentioned before, we do have a method of reducing that latency. However, this does assume that the wave is periodic and has a dominant fixed frequency, although our method does adapt that frequency depending on the historical data. However, we would like to consider alternative ultrasonic sensors that have variable frequencies, for instance. We can do frequency division multiplexing, and also look at sensors that have tunable powers, for instance, and also beam angles to test the differences for our sensing range. And finally, real-world evaluations. We unfortunately did not take this out to the ocean to test the link in those waves, but this is the next step. So we're working on making sure all the components are robust enough and ready to take out because we don't want to break them. Thank you so much. This is me testing the thing in the pool. And that's Chija on the left. I forgot to thank him in the paper, but he was a huge help, so thank you, Chija.
Varun Kumar from Carnegie Mellon. Great work, very amazing. Can you talk about what would be some of the ways you can deal with obstructions? Because you mentioned this fleetingly in your talk that, hey, we have the steering ability to sort of get around obstructions, but yeah, what's your plan?
Yeah, abstractions are definitely an issue in any sort of visible light communication-based method. I think the key difference between this and other VLC scenarios is that we do have that mobility. So we should be able to, in the next version, kind of adapt the aerial robot and underwater robot to kind of move around wherever those obstructions might lie. But yeah, that's kind of a fundamental challenge of visible light communication as a whole. Thank you.
Hi, Ish from UCSD. I have two connected questions.
Yeah.
One, you mentioned that the maximum throughput you are transmitting at 5 Mbps.
Yeah.
So for long range underwater communication, how will you improve, can you comment on how you achieve high data rates on this setup?
Yeah. So the biggest difference between our work and those prior works, which is related to this question, is that we have a relatively large beam divergence of our outgoing beam. So we don't have a perfectly collimated beam. In prior works, though, that were able to achieve those higher throughputs, they had a perfectly collimated beam, which they were then able to kind of steer to these large ranges. That is definitely something we're looking into to refining that beam divergence. And it's a little difficult with our mobile circuit, our mobile optical circuit. But yeah, that's definitely future work.
Yeah, thank you.
Thank you.
Hi, Colleen, Stanford University.
Hey.
You mentioned future work being testing it in a real-world environment. I was wondering if you had done any pre-thinking about, and you tested it in a chlorinated pool. How will that change because you have a salt environment and other sorts of particles like microscopic creatures dispersing the light?
That's a great question. We didn't fully investigate how different types of particles would affect this laser link. And I believe the prior work as well considered there were no, sand, for instance, or other things within the water. As long as the light can pass through it, there's going to be, I guess, some scattering as well off of these different types of objects. But if the light path can reach the receiver, we should be able to detect that data. But that's definitely something we need to consider going forward as well. Thank you for bringing that up.
All right, let's thank all three speakers from our last session.